My name is Eleanor O'Keefe, and I am from the Operational-Based Vision Assessment lab at Wright-Patterson Air Force Base. And I'm just going to be talking about changing a couple of variables in a stereoscopic remote vision system and the effects of those changes on both visual comfort and task performance. Just standard disclosure slide, we have to say anything I say today is not the opinion of the US Air Force or US government. Okay, so onto stereoscopic remote vision systems, or sRVSs. Their use is growing in industry, military, and medical applications. What are they? I'm sure most of you know, but I'm going to use the example of the aerial refueling case. So aerial refueling used to be done with operators looking out the back of the window. So this is the back of the plane. They would just look at the window and use joysticks to move this boom into the receptacle of the aircraft they're going to refuel. Now in newer aircraft, we have a stereoscopic remote vision system. So instead you have two cameras out the back of the plane representing the left and right eyes, or left and right imagery, and that is then fed into a 3D screen, and then you have your user with his nice 3D glasses, and he is able to see that real world scene sitting at in a more comfortable position at the front of the plane. So the design goal is obviously to make your image space, what you're seeing on your computer screen, match that of your object space, what is in the real world. But this is extremely difficult to do. So you can only do it if the setup of the cameras is exactly akin to the setup of the user's space, known as an orthostereo condition. And again, how much exactly does that matter? We want to minimize distortions. Do we have to get rid of them completely? We also don't know well what, if variable changes, how much they matter, and how much their interactions matter. A lot of times if you change one variable in your setup, it's going to change another one. Or say it can make your image space less distorted, but then if you change a different one, it will make it more distorted, things like that. So those are not yet well understood. And so kind of looking at these individually and looking for interactions is critical for understanding these sRVS systems. And again, we want to maximize performance, but also comfort of the user, because obviously their performance will suffer if they're not comfortable. Okay, so one example of a variable that you can make changes to in your remote vision system is your called camera toe-in. So you have to have a convergence distance in your visual sRVS, and one way to do this is to toe in the cameras or make sure that their optical axes are toed in, facing each other, so you get a convergence point. Here you can see, sorry about that you have your left camera and right camera slightly toed in, facing each other, getting that left image and that right image. And the pros for this is you can use all your camera sensor information. So another option is to use parallel cameras. If you do that, you have to shift the camera sensors. And to use that, you lose some of your camera sensor field of view. It's also just less computationally intense, so easier to do. The cons, however, are you get a vertical misalignment in your imagery. So then in order to fuse the top right of this image, you'd have to vertically diverge your eyes, which we're not really set up to do well. And you can't fuse the image completely because you can't diverge your eyes in different directions at the same time. Another con is you get this depth plane curvature. Just to note, all these, so this is an object space image, or sorry, an image space image, and all of these are based off of Andrew's famous 93 paper. And so one thing you get from camera toe-in is depth plane curvature. So you can see that here. This is all happening in your x-axis. So what basically in the real world, if something's moving left to right or right to left, but staying in the same depth plane, in your image space is going to look like it's coming towards you and then going back away, even though it's not in the real world. Another example is viewing distance. So how close you're sitting to the screen, to the 3D screen, is going to change your image space perception as well. I'm going to be specifically talking about near viewing distance here. So pro is you get that nice binocular stereopsis cue, so your binocular cue to depth. And that's been shown to be most useful at a meter or less. The cons are you get what's called depth plane compression, which is that you're compared to your object space, your image space is compressed, and also that compression can change throughout the image space. If it's one-to-one, it's not so bad, but if you get a change in depth compression across your image space, you're going to get velocity misperceptions, and then you're going to get incorrect size cues. And then vergence accommodation mismatch, which we heard all about this morning, so that instead of your eyes focusing and verging at the same distance like they do in the real world when you're focused on looking at an object, your eyes are converged at an object in image space, but they are focused at your screen. Okay, so we looked at these examples that I fortunately mentioned earlier in this paper. And we varied viewing distance and camera toe-in, both at two different conditions. So viewing distance, we had almost 1 meter, almost 2 meters, and camera toe-in, we had a parallel condition, and toe-in of almost 4 degrees. And these were crossed. So I'm going to go into what our image space looked like. So this is called our vision. These were developed through our vision modeling software, which we developed with vision products recently. So if anyone is interested in getting some use out of that, come see me at some point. So this is our far viewing distance parallel camera condition, which is the closest to ortho stereo that we had. And just to get you oriented, so these axes are in image space. The red ticks here are the same distances in object space. The color bar is just that depth compression metric, and the red line is the distance of the screen. So here is our far viewing distance toe-in condition, and you can just easily, this is just to show you that depth plane curvature that you're introducing with toe-in. And then here is our near no toe-in condition. And here you can see that more of the image space is closer to the viewer. And then also you're getting a greater variability in your depth compression, which just means that as objects are moving in depth, you're going to get a greater velocity misperception. Okay, so our particular design, just going over it really quick, we used a Sony 4K projector and active shutter glasses, so we used temporally interlaced imagery here. And we used a Flight Safety International image generator to show our simulated imagery. So unlike a true sRVS, we didn't have cameras looking at live imagery. We just used simulated imagery. And we have this task that we are calling our gripper task. So we have this kind of like it's a claw or gripper. It's holding onto a ball. And then we have this receptacle that's shown on our airport runway scenery. So the receptacle could move between -2 to +2 meters in depth, horizontally, and then in depth 6 to 12 meters. And then it was always placed on the ground plane. So the participant had to then use joysticks to move this claw or gripper so that and then when they perceived the ball to be directly over the receptacle, they went ahead and pressed the trigger, and then they got to see the ball drop to see kind of how close they got it. It would drop in the can, bounce off the can, behind or in front. Our Outcome variables for this task were Euclidean distance error, which was just the total error from the center of the ball when it dropped, or sorry, when it first hit the ground or the can, to the center, the very center of the receptacle. And then gripper arm velocity to give you an idea of how long their decision-making process was, which was simply the distance between the original position of the gripper arm and the receptacle divided by the trial time. So here we have a participant on our setup. We used a chin rest because we were using an iLink 1000 Plus to get eye tracking information. And that just helps stabilize the eyes. And then our outcome variables for this was we were trying to get a sense of eye strain through these variables. So looking at that, we were looking at saccade frequency, where lower tends to indicate less eye strain. Pupil size, smaller may be worse. I'll talk about this a bit later, but you can kind of go, this isn't the greatest measure. Pupil size velocity, lower is better. You're gonna get more eye strain if your pupil size is changing constantly. And then we had our visual comfort survey as well. Overall, we had 38 participants. They took 2 sessions of the task each time they came in, 30 minutes of the gripper task, then the survey, a 15-minute break, and then they completed another 30 minutes. So these were 2 different conditions they came in on a day. They also took that vision comfort questionnaire, which is based on a couple others in the literature, and looked at eye strain, eye tiredness, vision blur, and things like that. All right, on to results. So when we were looking at the distance error, we found that there was less error at the near condition than the far viewing condition. And looking at gripper velocity, again, faster decision making, we found that that was faster at near versus far. So here out of our performance metrics, being closer to the screen was better. Toe-in made no difference. Eye tracking metrics, saccade frequency, we got a huge effect of this. So near viewing distance, you had much greater frequency of saccades, about 5 times, indicating most likely increased visual strain, or eventually if you did this task over a long enough time, you would get increased visual strain. Pupil size, we found a smaller pupil at the near viewing distance, which could be indicative of eye strain. But we did find no change in pupil size velocity across the viewing conditions, which is gives you a hint that this isn't a good indicator. Another couple things is that our near viewing distance did have a bit of increased luminance. And also you have higher vergence accommodation mismatch at the near viewing distance. So what could be happening is the pupil could be getting smaller, it could be shrinking in order to increase your depth of focus when you're near. And if you're very interested in that topic, come to Eric's talk on Wednesday. All right, so what does this all mean? Viewing distance, trade-off, right? So it looks like your increased viewing distance is giving you better task performance. Why? Because I already talked about how near viewing distance is probably going to be worse based on the distortions in that image space that you're getting. Probably the benefits of stereopsis, that nice binocular 3D cue we get being closer, is outweighing those detriments. However, the image space distortions are likely causing then the changes in the oculometrics that we saw. So they're probably making the discomfort effects higher at the near viewing distance. So it kind of, again, depends on what you're designing your system for. Are they going to be, is it very important in small task performance metric. So if you do slightly better, is that very important? And are you using it for a short amount of time? So if you're doing something like aerial refueling or telesurgery, or explosive ordnance disposal, where you're going to be at that system for a long amount of time, eventually that viewing comfort is probably going to outweigh any benefits of increased performance. And at least for our task in particular, we didn't see a large performance change. Okay, camera toe-in. Nothing happened here. Why? Because it's normally, if you read the literature, it's pretty terrible. They tell you not to do it. And we've found that in previous research in our lab. So we've done a lot of stuff on aerial refueling work in our lab and have always recommended, please don't use this. It is bad. And you can see, so here I have the image space on the top right of the task we used in this study. The divergence here is only bad in the corners, and it's staying right around 5 arc minutes, which is the US Air Force standard. Our task was relatively low speed, so the receptacle itself didn't move, just that gripper. And it was mostly in the center of our field of view. So we were kind of staying within that center where the divergence is not as bad. Also, we used a kind of small amount of camera toe-in. Then the refueling tasks that we've done in the past, we have a dynamic task, so an aircraft's moving around the screen. You have this large boom that you're moving around with your joysticks. And then that also had a much larger camera toe-in, so you get a much larger divergence. We found up to 18 arc minutes. So your camera toe-in, the amount is going to affect performance. If you can limit it, it's better. We still don't recommend it. And then another take home is, so our lab is switching more to oculometrics and eye tracking methods to look for visual stress. We found no results in our survey, in case you were surprised why I didn't mention survey results. And so it might be because of our short task time that the survey results or any eye strain didn't reach subjective awareness. Most likely, the survey is just really bad at getting kind of people are bad at surveys. They can't give you like a good indication of their internal physiological state, which those oculometrics can get it at. Also, they're more sensitive. So we're seeing this crazy increase of COD frequency that we can measure already at a half hour of use that may not lead to visual discomfort until an hour of use. So we're already seeing that quickly. We don't have to have our studies along. All right. Conclusion, viewing distance, you get that trade-off between performance and discomfort. Camera toe-in generally be avoided. I guess if you're staying limited into that center of your image space and you have a tiny bit, it's fine. But again, we're recommending against it still. And some design variables can be considered independently, which is really nice during sRVS design. So we didn't see any interaction between camera toe-in and viewing distance, versus a lot of times when you change one thing in your sRVS design, it's going to interact with another thing to make things better or worse. So this is nice. You can set them independently, so that's good for designers to know. And then just overall, one thing we're finding more and more in our lab is that there's no one-fits-all design. This may sound disheartening, like, oh, we don't have a set of rules to go by, but it's actually exciting because you get to consider your use case. So what are you designing your system for? And then you can use research results, such as we show here, to best design your system.